So we will start the session in 5 minutes. So,
No problem, ma'am.
yeah. Hello. So I think we should start the session now.
Okay, ma'am.
Yeah, I was waiting for some other person. Okay. So recording has been started. She is already covered. So I would like to appreciate education sir for setting us down. So everybody is having any problem. So we are seeing the doubt through the lecture. So today we will start the session, week 11 live session. So we are having some specific questions. Like first of all, what is negative frequency and what is the significance of negative frequency at the same time? So like we never see negative frequency in actual real sense. Why is it the negative frequency means the negative time in the time domain? Is it the case? Some of these questions arises in our mind. So let us go through it. So first of all, negative frequency is a concept that arises in the mathematical analysis of signals, particularly in Fourier analysis. Fourier analysis means Fourier transform, because we have to see the time domain signal in the frequency domain, because spectrum is very rare in nature and that is very expensive. So we have to actually utilize it properly so that we don't have any wastage of spectrum in the frequency domain. So it may seem counter initiative at first, but it is a very useful tool for representing the frequency content of the signals in complete and symmetric way, because in time domain you have infinity time signals from minus infinity to infinity, so that you have to represent in the frequency domain. So let us consider a complex valued function ft, which represents a signal that is not a time limited, meaning it extends infinity in both the positive and negative time directions. So the question is, if you are getting frequency domain in negative frequency, does it mean that the time domain will also have negative time directions? So we will see that. So f omega, which is a Fourier transform, is equals to defined as minus infinity to infinity ft power minus j omega t dt, where omega is the angular frequency and I is the imaginary unit. We all know about that. So I'm going through a very basic. So okay, so now f omega is a complex function. So this one is a complex function, and that has both positive and negative frequency components. So what is the negative frequency component here means? So negative frequency component here is simply the complex conjugate of the positive frequency component, where f minus omega is equals to minus infinity to infinity. Here complex conjugate will minus to plus, it will come, and so it is defined as like this, negative frequency component. So where star directly means it is a complex conjugate. So what is the significance? The negative frequency allows us to represent the frequency content of a signal in a complete and symmetric way. For example, the positive frequency represents the positive content at positive frequency, and negative frequency represents the frequency content at the negative frequency. This is important because many signals have symmetric frequency content, and the practical applications are, by manipulating the positive and negative frequency components separately, we are able to selectively filter out certain ranges and some of the frequency, the cutoff frequency for a band pass filter, the cutoff frequency for the low pass filter. We will see all using some examples. For example, audio processing or image processing. So I will explain using some mathematics, like what is the significance of it, and does it the negative frequency implies a negative time domain, yes or no. So I want to know the answer from does it negative frequency implies negative time domain, yes or no? Just
Madam, just let me first state what I understand and where I find it difficult to visualize. Okay.
Okay.
First, time domain signals. Okay.
Yes, yes.
Time domain signals, in my view, they're always real. Okay.
Uh-huh.
So, but whenever we represent minus t, so that is only I consider as a point of reference with reference to the current, the
Yeah.
previous. There is nothing like a negative time. Okay.
Yeah,
So
yeah.
instead of starting from zero, so we can put zero anywhere, and from that point onwards, future is positive, and the backwards is negative. What happened in the past? Okay,
Yes, yes, yes.
so that is my understanding. So that is very clarity. That, in my view, that has got nothing to do with a negative or positive frequency, as you said. That yeah, yeah. Another thing is, so for example, the signal is a real signal. Let us say real
Yeah.
world. Every real world signal, when you have a Fourier transform, that Fourier transform is symmetric around y-axis. So, for example, let us say a sinusoid, pure sinusoid, with amplitude A,
Yes.
sinusoid with the frequency fc, let us say a carrier frequency. Okay, so if you wanted to represent in the time domain, it is a continuous ending from minus infinity to plus infinity, periodic.
Yeah, yeah, true.
To represent in Fourier transform, it is becomes a symmetric around y-axis at plus fc and minus fc, but with amplitude equally distributed, a by 2 and a by 2. Correct?
Yeah, true, true. Hmm.
Correct. So the concept of a negative frequency is only in the mathematical representation, but not, that doesn't have any physical reality.
Physical
At least,
reality it doesn't have, but I will explain like what is negative frequency in the time domain represents. So using some graphs and all, I have prepared for you. So yeah, you are saying very correctly. Like it's very correct that it doesn't have any physical significance in the time domain, but you will see the why the negative like why we use it. For example, first of all, it is used for the mathematical analysis, it is very sure. But what if we don't use, because in the bandwidth calculation also we used to refer only positive frequency. Like suppose you have some message signal, the message signal will have this one. So if we don't refer the bandwidth as 2 omega, otherwise else we refer the bandwidth as omega only. So this is the concept behind
oh,
it.
okay, okay. Wait a minute, madam. Again,
Yeah.
there is another of my related clarification. So, whenever we want to represent message signal, we are drawing a triangle. Why it should be triangle? It can be anything, right? Message frequency domain. Message can be any shape centered around zero, right?
Yes, yes, yes. You
Why
are.
we are always drawing triangle shape?
I'll tell you. This is actually asked by, I think question also asked this thing. So first of all, you have this amplitude and this is frequency. So in time domain, we generally refer this MT as either voltage signal or current signal. Suppose. So suppose this one is the amplitude of the voltage and this is frequency. So what happens? Whenever you increase the frequency, then the amplitude decreases accordingly. So that's why this is linear.
Need not be, madam. That
Yeah,
is
yeah,
not
yeah. Yeah, it
always.
is need not be, but for the communication perspective, it is not always the case. But yeah, sometimes even in fact this amplitude is always inversely proportional to frequency. Not always inversely proportional to
No,
frequency, but
madam, that is where I'm coming from. See, amplitude, frequency, and phase are independent quantities.
yes, these are the independent quantities. But whenever we increase the pitch, then amplitude. Suppose if we say very loudly, then the pitch comes at very lower range. It will come automatically to downer scale. So this is the concept behind it. Why we represent this as this one. Or that is also the video signal. If you see, the video signal spectrum is this one, 0 to 4.5 megahertz. Why it is this? Because video signal is composed of the images, which is actually the composition of the pixels. So here we don't require frequency and amplitude. So that's why here we don't consider. So I read this a very long back. So what you are saying here, it's correct in terms of the modulation perspective. This amplitude, frequency, and phase modulation, because these are in fact in carrier signal also. This one CT, the AC cos 2 pi FCT plus phi. Suppose if these are related, then why we don't consider this amplitude modulation, frequency modulation together? These are the independent quantities. You are saying very correctly, but in the spectra we consider this one just because of the sake of this.
No, maybe because I thought some representative instead of using any other arbitrary figure, I think as a conventional property.
It's conventional,
Yeah, because madam, one thing, if you say a general message signal MT, it can contain any number of frequencies.
Yes.
It can contain frequencies of any magnitude. For example, if you draw a triangle like this, I assume that at frequency 0, that means a DC component, right? Frequency 0, M of 0 is a DC component.
Yes.
Suppose in frequency domain, capital M of 0 is nothing but DC component.
Correct? Yeah.
So that means we are considering a signal where the DC component is very high and the high frequency component is 0.
Yeah, high frequency component is 0. Yeah.
But that is not a general signal. That is just a one case. But
like other every book's considered a different notation. Like the BP Lati consider this notation. I think
I understand. Only one thing which I need clarification is, okay, this is a representative some general notation for general message MT. Okay, we have to draw some picture.
Yes.
MT. So we instead of drawing that, we draw a triangle. Then that is okay.
Yeah.
So because in all our treatment, we always see, I see the triangles. So I'm just wondering why all the messages are triangles. No, it can't be. So different.
Like video signal spectrum is this one, 0 to 4.5 megahertz. It's rectangle.
Okay. Yeah. Okay. Got it. Okay.
This one is a triangle. Actually, this concept is given by some of my teachers. Like why we consider only triangle, because I was also this questioned, or I also questioned this why this is always triangle. Everywhere it is triangle, and but video signal is this rectangle. And I have to check, like some of my professors said this is inversely proportional, but yeah, these are all three are the independent quantities. That's why the modulation also we refer all these three as different modulation.
Yes, that's why we say amplitude modulation,
frequency modulation,
phase modulation.
Yeah. Yes, but the signals can't vary inversely proportional. I also agree to some point. Let's see what is the actual relation.
Okay,
so this
thanks, madam. And another thing that the triangle, so we always symmetric around 0. So that means actually you said 0 to 4.5. When you say bandwidth means we say 4.5, not 2 into 4.5, right?
Yeah.
We say only 4.5. B bandwidth of video signal means 4.5 megahertz only we say.
Yeah.
We don't say minus W to plus W, which is 2 W.
Yes.
Okay.
So this is having some significance. I'll let you know. So moving ahead, for example, XT be a complex signal. Suppose this is, which varies from minus infinity to infinity. So what is the Fourier transform of this one? So the Fourier transform will be 1 by 2 e power minus j omega t. Sorry, it can be represented. XT. So x omega or x j omega. So we can represent this one as 1 by 2 e power minus j omega t plus e power j omega t. Okay, you know this one, the formulations. Then after doing the Fourier transform, we know that this will be the shifted impulse at positive frequency and negative frequency, F0 and F0, or simply if we can say in omega domain, then pi or del omega plus omega naught plus pi del omega minus omega naught. So these two vectors we will deal with independently.
Yeah. And another thing, madam, just
Yeah.
sorry that it is not related to this, but
Yeah,
related to
yeah.
the way representing domains. Okay, just whatever you have shown, omega domain.
Yes,
See,
yes.
another clarification is always we shuffle from F domain to omega domain. Simply we substitute omega is equal to 2 pi F. For example, the equations I always get confused. 1 by 2 pi is required or just not required. When we require 1 by 2 pi, when we don't require 1 by 2 pi. So, okay.
Yeah.
Yeah.
So,
So,
yeah,
you
yes,
can give me
yes.
some clue actually how to remember. So,
So,
actually, Aditya sir started with F domain completely.
hmm,
So, but somewhere, actually, when it is in F domain, we don't get into 2 omegas, sorry, 2 pi. Okay. Just to show me one transformation in the above, actually, can you just scroll? Just now I saw that. Yes. Yeah. For example, delta of F plus F0. That below you convert it to omega domain, right?
Because
So,
omega is equals to 2 pi f.
yeah, omega is equal to 2 pi f or f is equal to 2 pi, f is equal to omega by 2 pi, right? Yeah,
Yeah.
omega by 2 pi. So
Hmm.
when you substitute f in omega by 2 pi, omega, so 2 pi comes in the
Hmm.
denominator. No.
No.
No, no, no,
F is
no.
equals to, what is
Omega.
that? 1 by 2 omega is equals to 2 pi f. So
Omega.
this is f domain. So we will multiply this one by 2 pi. So here we are getting. If you multiply by 2 pi, then here
Just
we are
multiplied by
getting.
2 pi, then what happens? Yeah, 2 get cancelled and pi comes. Okay. So that is how we convert from F domain to omega domain language.
Yes. This is what. And if you are having some confusion in some domain, just we know this is, sometimes here it is written like this:
Ah,
j omega, x
right,
omega,
right.
xf. These
Yes.
all mean the same thing. Frequency domain.
How to convert one from the other? That is it.
Frequency transformation.
No, I know
Huh.
one is a plain frequency, other is a radian frequency, but
Yeah.
convert one from the other. Which formula I have to remember?
Oh, okay. So sometimes, yeah, no. In fact, DTFT is also frequency domain representation. DFT is also frequency domain representation. But sometimes, but some way or other way, we can say DFT is faster than DTFT. Formulations are different, but all these are the frequency domain representation. For example, jet transform is also frequency domain representation.
Yeah.
Laplace is also frequency domain representation.
I got it, madam.
Yeah,
In the
yeah.
frequency, the notation F and omega, that is where I get confused.
Yeah, F and omega. So you are
Ah,
saying this one, na? F and omega.
I'm getting
Okay.
confused. Sometimes in some books we use the F and some books we use radian frequency.
F
Okay. How
and
to easily
omega.
convert from that, from one
So
formula?
if you have this XF, you multiply this to 2 pi.
Okay.
You will get, oh, this is the formulation.
Okay. Yeah. Okay. Similarly, in the Fourier transform also, if you use the omega notation, then some additional factors will come 2 pi. So that is, yeah.
Yeah, so in that sync formulations and all, you also get confused now.
Yes.
So, for example, you have this one. What is that? Tau by 2 to minus tau by 2 A. Then A tau sync F tau. I will definitely suggest you to go with F. Whenever F is there, you multiply by 2 pi. Then you don't have any issue with that. Yeah. So A tau sync F tau, it is the formulation. For example, if you want to convert into omega, so what you will do? Here A 2 pi sync omega tau.
No. Sync F to omega multiplied by 2 pi. So to multiply by 2 pi, then it becomes.
See, here we have to multiply everywhere. For example, A tau sync. Sync means what? Sine pi f tau. So pi f tau. So here also f, he's here, na? Sorry.
Yeah.
So here 2 pi sync the pi will also get cancelled.
Excuse me, ma'am.
Yeah, yeah,
Excuse me,
yeah,
ma'am.
yeah.
Ma'am, I think we will divide by 1 by 2 pi when we will go
Here,
from f to omega 2. Yes, ma'am. Here it will be 8 tau divided by 2 pi sinc function.
why omega is equals to simply 2 pi f, right?
Yes, ma'am. Omega equal to this much, but when we are doing it in omega domain, then it will be equal to 1 by 2 pi times d omega, right?
No, no, no. F is simply omega by 2 pi. For example, let us see by just formulation. We are getting confused. Minus infinity to infinity f t e power minus j 2 pi f t dt, right? This is f x of f, right? If
Yes.
we write x of omega, so what is
Yes.
that? Minus infinity to infinity f t
Of omega.
j omega dt.
Yeah.
Here we don't have any formulations. Okay?
No, 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 no. There should be some factor, right?
No, no, no. In inverse we will have factor. Here we don't have factor. There is a reason behind it, because here we are not differentiating with respect to omega and f. Here the term is t. So it will not affect, because 2 pi f we are simply representing here as a omega.
Okay, okay, okay.
So here I will add one page where I am adding page. So let us see the inverse form of it. So how will you write xt? So
Equal to
simply
minus
xt f x of f
x of f e to the power of j
2 pi
f
ft df.
df.
Huh.
Yes.
So xt in terms of omega, it will be minus infinity to infinity x of omega e power j omega t d omega. Here you are having omega, so in fact to convert this f to here, it will be multiplied by 2 pi. So of course you are getting confused, because here you are taking this df to d omega.
Okay.
So
Okay, ma'am.
it should not have some multiplication factors. So that's why we are dividing it to 2, because see, however we are converting this to 2 pi df, right? 2 pi df. We are multiplying by 2 pi only. But here too, in order to have only not this factor, we are dividing by 2 pi. So this one is 1 by 2 pi d omega.
Okay.
Yeah, so df to d omega will be multiplied by 2 pi only, but you have to make sure this the constant comes between. You have to overcome that. So the simple example I have given you, sir, here. So this one, this is the Fourier transform, and this is multiplied by 2 pi. You are getting this one.
Okay.
Yeah, so I think you people don't have an issue in that. Sometimes I also get confused in this, but it's okay. I will just suggest you to go with f. F is good, and pi and 2 pi doesn't have any effect, because the sinc function and formulation also I have memorized in terms of f. But whenever that omega also comes, I can do by some formulations and all. So this is what about negative frequency we are going to do. So here you can see this is one of the rotating vector and this is one of the rotating vector. So I am telling you the negative frequency corresponds to just the direction of the rotating vector. I'll let you know. So for example, this is real and imaginary plane, and where you have this one, which is magnitude is having 1. E power j omega t magnitude, if you find it, it will be 1. So this is 1, and what is the angle associated with it? The angle will be omega naught t. So the direction it will take is anti-clockwise. Or for example, this magnitude, which is this vector, which is e power minus j omega naught t. So here you will take the magnitude as 1, but the direction it will take as counterclockwise. Now we will see through one of the example given below. So you know this is what we plot for the frequency domain, but here it is a magnitude spectra. This is a phase spectra. Sorry. So in frequency domain, you will have two spectra, magnitude and phase spectra. The magnitude spectra is having the property of even function. Why even? Because it is symmetric with respect to y-axis, and odd and the phase spectra is having the property of odd function. Why? Because it is having the symmetry with respect to origin, like this. So magnitude and phase. Okay, so I'll just give you one example here. You will not have any issue with that. So this is a so for example, if you, yeah,
madam, for example, if it is a pure cos sinusoid of cos function a cos omega t,
yeah,
so that also will have that is anyway even function.
that is even function. It will only have positive frequency.
Yeah, it will only have, but
Yeah, I'm telling you that the cos function is having the exponential terms of both e power j omega t plus e power minus j omega t.
no, but even sine also have both, no?
Yeah. That is also having both.
So no, what I'm trying to say is, suppose if you plot magnitude plot of both cosine sinusoid as well as sine sinusoid, both look equal, magnitude plot.
Yes.
Except phase plot is different, right?
Yeah. The phase plot is different.
For example, by looking at the magnitude plot, we cannot say whether the sinusoid is a cosine sinusoid or a sine sinusoid. Can we say? By looking at the magnitude plot frequency domain?
Yes, the magnitude plot of frequency domain in sinusoid is what?
Yeah, just to draw sinusoid. I'm talking about sinusoid means sine.
Yeah.
Sine function.
This is magnitude plot for cos. This is a magnitude plot for cosine.
Oh, okay, different.
Yeah, it is different, no? It is having 1/2 power.
Ma'am, excuse me, ma'am.
Yeah.
Excuse me. Ma'am, but here in the sinusoidal plot, we are taking care of this angle also, like it is -1/2, phase should be 180,
Yeah,
right?
yes, because you can write now this one x f minus omega naught. What is the
No, ma'am, but if we plot only the magnitude of this component, frequency component of sine, then it will look
no,
similar.
I'm telling you individual frequency component. Suppose, yeah, positive and negative frequency is considered, like it is a magnitude with at that frequency. Suppose this is at this negative frequency, you have magnitude of what? Negative. I'm telling you why this is magnitude spectra, because it is plotting the magnitude at that particular frequency. If it is plotting the phase at that particular frequency, then it will be phase spectra. So you are not saying that all the negative sign you have to take the positive sign. This is not the what magnitude. Like what is?
Ma'am, but normally what we do that for negative, we take the magnitude.
Yeah. That is different. That is different in frequency.
Madam, this confusion is in most of the representations. Always magnitude is always positive, and negative frequency as positive frequency, magnitude is always up.
Yeah. I can understand, but
what you are saying is for pure sinusoid of sine function, the magnitude plot is on the positive side up and the negative side is negative, right?
Yes. But it is actually giving the magnitude at that particular frequency component. Suppose you have the frequency and at a different frequency you have different magnitude. It's just the impulse function at positive frequency f0.
There is only one frequency anyway, f0. For,
Yeah. Frequency. That's why. That's what for this cos omega naught t is can be represented at 1/2 e power j omega naught t plus e power minus j omega naught t. So I'm telling you this is positive and this is negative frequency. So
just write sine omega t.
Sine is 1/2 j e power j omega naught t minus e power minus j omega naught t.
Okay.
Sine omega naught t.
Okay. So when you plot magnitude plot of sine omega naught t, at the negative frequency, the magnitude is negative.
Yes. See, however you will have this j. This j terms to.
Okay.
Okay. Yeah. So this is what about magnitude spectrum. However, I want to tell you like what is the significance of negative or positive. So in both of the components you have this e power j omega naught t and e power minus j omega naught t. Okay. So what is this? So this one is a rotating vector. So it is rotating with the angle of omega t. Okay, plus omega t, and this is minus omega t. So let us see. So this is a rotating in positive direction. Positive means anti-clockwise and negative means clockwise. So this positive direction corresponds to positive frequency and negative direction means corresponds to negative frequency. So let us see how it affects the time domain. So if you plot in real and imaginary axis, you have this e power j omega t with the angle of omega t. Let me take different color. So with angle of omega t, and here in fact in time domain, this is the amplitude which can be voltage. Take different color. It can be voltage. It can be current. So here it is amplitude. Amplitude means magnitude, which I refer it in that particular case. This one. So here, but it is in the time domain. So this e power j omega t will have the sine function with this particular frequency. So this is cosine. We were representing as cosine. This one, cos omega naught t. This one. We are taking this example. So here it is cosine. So it is starting with 1. Let me take different color. Yeah. So it is starting with 1. Okay. So let us see. At this particular point, this is omega t is equals to 0. So here it is corresponding to 1 amplitude. So it will go like this. This value corresponds to this value. Okay. So and finally this value corresponds to this value. And if this goes like this, so this value again corresponds to this value. So what we are seeing here, the one circle means the one period of this. Why period I am saying? Because here the 1 again comes 1. So it is completing one cycle in time domain. This is one out of one rotation in time domain. So I am just bifurcating each of the terms of the cos omega naught t in time domain itself. So this corresponds to positive frequency we saw in the magnitude spectra, right? Similarly, if we take this particular rotating vector, which is e power minus omega t, which is a second term in the cos omega naught t term. So this is what we are seeing in the time domain. Okay. So here it is amplitude. So here we know this will work like this will work clockwise. So let us see this particular value. It will correspond to this one. If we see this particular value, it will correspond to this one. The same rotating will correspond to other different values also, but we are considering one rotation. This particular value corresponds to this one. This particular value corresponds to this one. And finally, this again corresponds to this one. So what you are seeing here, this one is this one. This is one cycle. So here in the negative frequency in the time domain corresponds to positive frequency itself, because positive time domain itself, because we are not taking any negative time domain. So what we are seeing here, the terms which corresponds to positive and negative frequency in the frequency domain that values correspond to positive values in the time domain itself. So we are not taking any negative time domain. So here what is the answer? Negative f doesn't imply negative t. Why it is this? Just negative frequency removed by the process of projection in time domain. So what we are doing, these values are corresponding to projection, and negative frequency is just a vector spinning in this time domain.
I got it.
Yeah, so this is all about the time domain realization.
So that means we can make a statement for any real signal.
Yeah.
Okay. When we have a frequency domain, we have a symmetric about y-axis, right?
Yes.
Yeah, symmetric about y-axis. Both will have plus exactly symmetric. for real signal, any real
Yes,
signal.
yes, yes, yes,
There is
yes.
nothing like a real signal having only in the frequency domain only positive side. There is nothing like that. All both
Ah,
will be equal. It's
yes, yes,
it
yes, yes, yes.
balance out, right? When you
It
it's
balance
just,
out.
yeah, that is a representation actually. That is a representation.
Yes,
It
at
can
that
be
too, you're having some issues with some factors with that, because in mathematics we are representing it as a sum of two rotating vectors, and one is
exactly.
corresponding to positive and the other was corresponding to negative. And in fact, if we plot if we correspond with particular values in a time domain, it is just to balance it out. So we
Yes.
can see it is getting removed by the process of projection. It is called the process of projection in time domain.
Yes, yes, I got it. I got it. I got it. Okay,
Okay.
man. Next
Oh,
one. Yeah.
yeah. So next topic was baseband versus band pass. So KG Krishnan sir asked this question. So I will let you know what is your understanding till now.
I will tell you. So
Yeah.
generally baseband means I understand. For example, speech signal is there. We say speech signal contains frequencies from 0 to let us say 5 kilohertz. Okay, speech.
Hmm.
Okay, so we say the
Hmm.
bandwidth of a speech signal
3
is
hertz
5
to
kilo.
3.5 kilohertz are zero, we can say. Yeah, yeah.
Okay,
Uh-huh.
0 to okay, starting from 0 also later 0 to
Hmm.
5. Let's say 5 kilohertz
Hmm.
as a bandwidth of the speech signal. Okay,
Hmm.
so that means when we plot that on the frequency domain, um, that so we plot -5 to +5, right?
Yeah.
Correct.
Hmm. So I just want to tell, like, I think sir, you were absent in one of the classes. Should I explain this band pass broad and this baseband? You were there in that class, no?
Yes, ma'am. Yes, ma'am. Actually, baseband is something which has not been processed or altered. It is in the form of base, original frequency spectrum, right?
Ha ha ha.
Band pass. When we have shifted this baseband signal to some higher frequency, and broadband, I don't remember.
Yeah,
Acha
yeah,
acha.
yeah, yeah. I also got it. So baseband means centered around zero, zero, zero,
Yes, yes, yes,
zero
yes.
to plus 3.5 or 4.5 megahertz, whatever it is.
Mm.
So pass band means something shifted far into the right.
Okay, nice. You are getting this one. I'll just draw the this signals and I'll let you know. Before that, I want to ask one more question. This the broadband, you asked one question also. The broadband. So broadband is similar to wideband. Kurshid, broadband is similar to wideband. And what is difference between broadband, which is also known as AK, also known as wideband, versus narrowband?
Wideband versus narrowband, ma'am. I don't remember.
अच्छा अच्छा
Uh,
कोई नहीं
I will interpret that way.
या या
Broadband means the bandwidth is much bigger than the narrowband signal.
bandwidth is much bigger. Okay, we'll see. So for example, let us consider again this cos omega naught t. This color is visible now. So
Yes.
yeah, so 1 by 2 e power j omega naught t plus minus omega naught t. So let us just take the, if it is xt, then xf, it is 1 by 2 del f minus fc plus del f plus fc. Okay, so this this is this is the carrier signal which is used for the modulation. Okay,
Yeah.
so why I'm telling just again is something. So this is used for modulation. For example, if we have this mf without modulation, and this is what w minus w. So this is after modulation, it is getting shifted. This is fc, this is fc. Let us take this as f naught. So fc plus f naught Fc minus F naught, and this will be minus Fc plus F naught minus Fc minus F naught, and the amplitude will be 1 by 2. So this particular signal without any modulation is known as baseband. So it is the term is defined in terms of modulation only, and this is baseband, and this is MF after modulation, which is generally AMF. It is band pass. Why it is baseband and band pass? Because the base is there with him, with this signal, and here band pass because we have to require this particular band pass filter to have this particular band. So that's why the band pass name is given to this particular signal after modulation. And in fact, if we see this band pass, this band pass signal is also known as narrowband signal, and this baseband signal is also known as broadband or wideband. Why it is this? Because the higher frequency component, which is F naught, divided by lower frequency component 0, is infinity, and here the higher frequency component Fc plus F naught divided by lower frequency component Fc minus F naught, somewhat less than 1.
Yes, ma'am.
I explained this one.
Yes,
So
ma'am.
this is the terminology for baseband and bandpass in narrowband and wideband. In fact, in narrowband we also have seen NBFM, narrowband frequency modulation. Why we have considered that? Because in after modulation we have this particular thing.
Oh, okay. As I understand, without modulation, it is called a baseband signal. After modulation, we call as a pass band.
Yeah.
Pass band, band pass, both are same.
Same.
Okay. And that also is called a narrow band.
Narrowband, like the modulation is the process to convert the wideband signal to a narrowband signal, because the highest frequency component to lower frequency component somewhat is lesser as compared to highest frequency component to lower frequency component here.
So narrow band. Okay. That means we are reducing the band, is it?
Yeah, the thing is, yeah, we have to, the band we are reducing, but we are converting all the signals to higher frequency so that the attenuation process gets slower, and the scattering and the reflection, all this process will reduce, and at the same time antenna height gets reduced. This is why we do modulation.
Somehow it doesn't make intuitive sense. For example, on the left hand side, you said that is a baseband signal, I understand. Whatever, for example, I speak to a microphone, and that is a pure baseband signal, right?
Yes.
Okay, and that you are calling as a broadband. That doesn't.
No, it is a broadband, and all the naturally occurring signals are also known as broadband.
Oh.
Because these all are analog in nature, and we have to convert that to a particular frequency so that we can actually nowadays we are converting to this particular frequency, which is FR1 and FR2.
Okay.
So this is less than 6 gigahertz. This is greater than 6 gigahertz up to 39 gigahertz. So this is also known as millimeter wave frequency. We are converting to higher and higher frequency to have particular application. Like this is helpful in beamforming and all MIMO, these things. So that is why we are all the naturally occurring signals are broadband in nature, and we are converting it to narrowband to have particular application out of it. And that too FC varies for different modulation.
Okay.
Yeah, so I think this gets clear. Now moving to the next question, which was the frequency modulation versus phase modulation. So yeah, the frequency modulation and phase modulation are very similar and directly proportional to it, and we will see how it is proportional to it. So the actually angle modulation and amplitude modulation. In angle modulation we have frequency modulation and phase modulation. So if we see the carrier signal, which is AC cos 2 pi fc t plus phi, then this particular thing can also be called as a phase. Now in PM, ST is equals to AC cos 2 pi FCT plus KPMT. Now I want to know the unit of KP and KF. First, let me know about this. Then we'll see the difference. And in FM, ST is equals to AC cos 2 pi FCT plus 2 pi KF integration of MT dt. It is defined in standard term, like in AM also we have defined. So basically, sir, you were asking the difference between that. We are actually changing the phase of the carrier wave with some amount which is proportional to the message signal, and here we are changing the frequency of the carrier signal by some amount that is which is proportional to MT. Can you tell me the this unit of KP and KF?
KP. KF means the sensitivity, right?
Frequency sensitivity and phase sensitivity.
Okay. Okay.
Ma'am, what is the unit of this message signal first?
You can assume as voltage.
Okay, then it will be volt inverse radian per second, kp.
And KF?
Kf will be, ma'am, radian volt inverse. Yes, ma'am. Radian volt inverse, and this message signal also there. Per second square it should be.
Okay. You are actually saying unit of KP, very correct. Here, just trying to analyze it. See, this is the unit of radian. So it should also be having the unit of radian, right? So KP will have the unit of, what is the unit of KP?
Volt inverse radian per second.
Radian, volt. What is the unit of that? Radian, it is a unit. The angle is radian. So this is.
Okay, ma'am.
So similarly, here we are not changing this radian. We are changing the frequency, right? So what should be the unit of this KF? KF should have the unit of
Frequency by voltage.
yeah, this one.
Yes.
Okay, ma'am. Okay.
So this is the difference, basic difference between this, and we will see the mathematical formulation associated with it. So we know that the phase of any system, either it can be oscillatory system or LTI system or any system we have seen till now, can be defined as the omega into t, which is omega is the angular frequency multiplied by t. So 2 pi f into t. This is what. So the phase, it's a proportional to frequency. Now if we differentiate this phase, we know that the phase itself depends, it's a function of time, and frequency itself is a function of time. So if we differentiate phase with respect to time, so d phi by dt you will get this particular t, 2 pi ft, f by ft, because f is also a function of time. So if we write f in terms of phi, so this will be 1 by 2 pi d by dt of phi t. So phi t is nothing but 2 pi integration of fit dt. So if you see here, we are writing it kpmt. If you just replace it 2 pi, this particular formulation, in this one, you will get fm. So in this way, PM and FM are directly related. And now I want to know how, if you have PM, how we will generate FM, and if we have FM, how we will generate PM. So you have to draw the block diagram accordingly. Are you getting this point? This one. So why there is a difference between this one?
Yeah, it looks to me that one is integration of the other kind of.
Yeah. So here in this formulation, if you just replace this Kp to Kf and 2 pi Kf integration of mt dt. And one more thing you want to know, I want to tell you, like in modulation, whatever parameter you are changing, that parameter should be directly proportional to mt. In why? Here also the parameter is directly proportional to mt, means directly inclined with mt. because the message signal we have, and the message signal, the carrier, the what we say, the characteristics of carrier should be changed in accordance to message signal. In fact, in amplitude modulation also, what was the formulation? AC 1 plus KAMT cos 2 pi f ct. Here also this K multiplied by MT.
Madam, anyway, that's a different question. In
Yeah,
amplitude
yeah.
modulation, I got a question.
Yes, yes.
Why we are adding a carrier to the modulation again? Okay. So 1 plus, that word, why 1 plus? Simply AC, simply AM multiplied by KP multiplied by M of T multiplied by cos, no? Why 1 plus? That,
So you remember we have the amplitude modulation DSB, SSB.
yes.
So in DSB we remove that 1 plus, right?
No, but why itself, first of all, why we defined like that in the beginning? In the beginning,
Okay.
pure amplitude modulation, we defined in the.
So AC 1 plus KAMT cos 2 pi FCT.
So for me, if I go by my understanding of what modulation is all about, is a multiplication of message signal by the carrier signal. Message signal is M of T. Carrier signal is AC into cos 2 pi FTCT. Simple.
Yes. So see, this is MT. It is low frequency. Sorry, MT. This is low frequency component MT, and you have this one as CT carrier. You have this one, this one, this one,
Yeah,
this one.
simply multiply. Simple.
Yeah, simply multiply. But why we are adding this? Wait a second. So here you have battery saver. Wait a second. Here you have this one, this one, this one, this one. Here you have this one, 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 this one. Yeah. And 1 plus K, 1 minus K. So basically, this is defined for the modulation index. Like modulation index, you know, what was that? How we will define modulation index? A max to A min. Right? Which was what? 1 plus Ka modulation of MT, 1 minus Ka MT. So actually the thing is, the amplitude it will having, it is actually the amplitude modulation. So okay, so initially we are representing with respect to 1 because the initial point should be shifted by something, and the reason of this I am not remembering properly, but I think it is to boost the amplitude sensitivity of that. I have to check it, but yeah, some reason is there with that. Wait a second, I have to.
See, actually, in the pure amplitude modulation, we have 3 components. We have carrier is there, upper envelope or upper sideband, and lower sideband. 3 are there, right?
Yeah.
Okay. Slowly we remove in the later on in DSBSC, we will remove the carrier. So
remove the carrier because power is getting confused in that consumed.
My just intuitive question is, why in the first place we did we include carrier in the first place? Carrier doesn't convey any information. Why it is there in the first place?
Yeah, it is true. It is there in the first place because it is getting transmitted along with the message signal in order to have the modulation.
Okay.
You have to analyze it, where the power is getting consumed and all, like what is there in amplitude modulation. So that's why we pass it.
Okay.
So because in initial case also you have seen like what is the power, and you have seen that 50% up to 33% only we can achieve the efficiency.
Yes.
So that's why we are getting improved, and there is a application of AM also somewhere. Audio broadcasting, I think. Video broadcasting. Amplitude modulation application, video broadcasting. Like whenever PM Narendra Modi ji sir has to say anything, then he will say through amplitude modulation. Why it is that? because
Radio.
because the frequency I think it is tuned to it, and one more the range. Yeah, the range is also.
Range is more.
Ha
Basically,
ha.
range of AM is more
Yes. So
than
it is
FM.
used for the and whenever the noise part come into the picture, then since noise is directly proportional to frequency
Yeah.
amplitude.
My question is,
Yeah.
this traditional AM modulation used in broadcast radio,
Yeah.
why are they using? They can use simply SSB, no? Saving a lot of power.
No. Yeah, saving lot of power also, but SSB requires filters also, filter design. SSB used for exclusively for voice. SSB is used exclusively for voice. There's also a reason behind it. Voice signal is having the frequency spectra like this,
Okay.
3 hertz to 3.5 kilohertz.
Okay.
This one. And so in actual real sense, if you want only one SSB, one this band, so you have to make the particular filter accordingly. The filter design for SSB is much easier than DSB and all. So you require this one only, this particular. And the gap is also 6 hertz.
Okay.
So you have to take care of this. There is some standardizations going on, but yeah, it is used for this. This is used for this. SSB is exclusively used for voice signal, and AM is used for video broadcasting. FM is used for FM radio 80 hertz to 108 megahertz. So this is the application for that. So I will let you know like why 1 plus is added. There is a reason behind it. I'm not remembering properly. It is written in my copy. Okay.
Okay, madam. I got it.
Yeah. So yeah, can you tell me how will you get PM to FM and FM to PM?
See, if you want to get PM from FM, you have to integrate FM.
PM from FM. We have to differentiate it, right? Suppose we have FM. So you have to just take dt by dt. You will get PM. If you have,
Rate
yes.
of change of phase is frequency. Right?
Here you are having integration term. So that integration will get cancelled by dt, right? We have integration term. Just let me know is it correct or not. Question?
Yes, ma'am.
How we will get PM to FM and FM to PM?
Yes, ma'am. I'm actually looking into it. I'm not yet sure.
Acha. But I'm sure this is the way we can get. So if you have
frequency modulator, we will first differentiate the frequency, right?
yes.
So if we will get 2 pi.
And it is the most commonly asked question in the exam also. So
Ma'am, theta, excuse me, ma'am, phi
Yeah.
is equal to 2 pi times f, right?
you remember this one, na?
Yes,
That
ma'am.
is-
Yes, ma'am. Actually, this is correct, ma'am.
Ha.
Yes, ma'am.
So in this way PM and FM are related. So I think sir this question also gets resolved, like you asked this question.
And here we will first integrate it, and then through phase modulator we will get. Yes, ma'am. Both are correct.
Yeah. So I think we should move to the next question. Sir, is it clear now?
Okay, madam.
Yeah. So now you asked me some LTI examples and
Yeah, so
Filters.
I wanted to have a clarity on signals and system. For example, M of T is a message signal and carrier signal. See,
so modulators we will also see
Yeah.
later. First let's see the filters. So if we have the low pass filter.
no, let me make a general statement, then you can validate.
Okay,
So,
okay.
any LTA system can be considered as a filter, correct?
any LTI system can be considered as a filter? No, but this particular filters we are considered as a LTI system, because LTI system should have properties, no? So that property should be followed. Then only we can say it is a filter. It is LTI system. Any filter we can consider LTI system.
Filters are represented as an LTA systems.
Always,
Man,
yes, yes,
this
yeah.
one is IIR type of filter, right?
Yes, yes.
Yes.
So IIR filter. Actually, I asked Abhishek also, like when he is going to cover filter, so he said that he'll cover in the next. But yeah, for some examples, I have taken some examples like how we will say this is a low pass filter and high pass filter. So this is what an example of LTI low pass filter. Yeah, every filter can be considered as LTI because it has that properties.
My next clarity is modulator. Okay, modulator is nothing but multiplication of signals in time domain.
Yes.
In time domain, right? So that multiplication process is simply a multiplication. Then it is not a system. So in a filter, you input a signal and the output is a filtered signal through the transformation of h of t, right?
Yes.
A filter always represented as an LTA system with h of t, frequency response of the filter h of in time domain h of t, in frequency domain h of f. Okay, so there is an input signal x of t and the filtered signal is y of t.
Yes.
So filter is a system. Okay, there is no doubt about it. Correct? Filter
Yeah.
Filter is a system.
So anything which can be represented in terms of transfer function, it can be called a system.
What about modulator? Modulator, is it a system? Modulator we are simply multiplying.
Yes. We can write it as a modulator, as a system. Why? Because see, you have HD. Input is empty. You are getting output as this, as suppose AM itself. So what is that? AC 1 plus KA MT cos 2 pi FCT. So this YT divided by MT can be write in terms of HT. This is a question.
No, because that is not an LTA system. That is not a system. What I mean is system means LTA system.
It is not LTA system?
Because LTA system output is always a convolution of input and
No. Convolution. Okay. LTA systems output also convolution.
But we are interested in multiplication systems.
Wait a second. It's AM and FM are not LTA system. Let me see.
See, okay.
Yeah. It is not. It cannot be a LTA system. Then every LTA system has this property, convolution. Yes. So we cannot write. It's just a system where it is not LTI.
Actually, we represent as a multiplicator symbol, cross. That is not a system. I think it is a multiplier. Simply multiplies two signals.
Okay. So, fine.
Symbolically, in our diagrams, we represent as a cross, right? Circle and cross to circle.
Very true.
So that crossed circle is not a system. It is only an operation.
Yeah, it's an operation in time domain. So modulation is not an LTI. The process is not LTI. True.
Yeah, actually, it is a multiplication in time domain, but convolution in frequency domain.
Multiplication in time domain, convolution in frequency domain. So it can represent an inverse LTI, you're saying?
Yeah. So for example, you make a block diagram, rectangle. Okay.
Yeah.
Yeah. And then input is M of F. just a rectangle block.
Yes.
Yeah, and input is M of F, capital M of F, and output is Y of capital F, and in between is H of F. Let us say is carrier. It is a
Okay.
carrier. It is a carrier. Okay, C of F. Okay.
Uh, So,
Now we can say this is a modulator. C of F
okay.
is a C of F is an LTI. I don't know. I'm just
We also didn't see like this.
actually, madam, you say Y of F is equal to M of F convolution of C of F.
Huh.
Right? You can write that Y of F is equal to, correct, right? In frequency domain, the
Have you read it this anywhere, sir?
no, I have not read. I actually yesterday, today we started reviewing it. I'm reflecting, intuitively trying to understand each and every word. So I got these doubts. So
Yeah.
I said, what is wrong with this statement? Okay, we put a box there, C of F. Okay, actually speaking, it behaves like a transfer function, right? C of F.
Um, See, transfer function is also is only defined when we have initial condition as 0. This is also the case. Here, do we have initial condition as 0? We have to see. Memoryless, invertible, linearity, all things must be
Yeah.
defined for the
Yes,
LTI.
ma'am.
Yeah,
Yeah.
yeah.
Ma'am, what are actually we trying to prove here?
So, sir is having doubt like modulator is not an LTI system.
Okay.
Then
So
it's yeah, yeah, sir, say.
yeah, what I'm trying to Manoj sir is modulation is nothing but convolution in frequency domain, correct? So if you have this block, and in the block the equivalent for transfer function is a carrier C of F, and input is M of F, and the output is modulated signal
Sir,
Y of F.
sir, I think in the case of amplitude modulation that will be linear operation, but in the case of frequency or phase, we can't be sure about that, right? In
Yes,
the
and
representation.
also one more thing, along with linear time invariant should be there. LTI, time
Yeah,
invariant should be there.
as Minaj said it, that is right. In case of amplitude modulation, it works. This
Yeah,
is
this works. True, true, true. That's what today, when I was saying some examples from the book, I got the example for the AM, but I didn't get for the FM and PM. I was I was thinking about it. So I think the AM is somewhat
so
lenient. But yeah,
so
in frequency domain it is LTI. Uh,
frequency domain, it is an LTI. Okay.
Time domain. No, no, no. Again, then the definitions it will different. Sir. I think it is a linear time invariant system. Time invariant. So it will be linear frequency invariant system.
Madam, okay, I understand where we are going. Let us move forward. Okay.
Yeah. So I have to see. I also don't know like
Because so when I'm actually, madam, in fact, parallelly I'm doing signals and systems. That is why. See, I want to trying to correlate and make a meaning out of this usefulness. So I am see always my mind is juggling between time domain, frequency domain, time domain. So I wanted to have some we call signal, sometimes we call a system.
hmm.
But when you represent a notation H of H of t can also be considered as a signal also, but when you written in an equation or as a I don't know, maybe
Yeah, yeah. So you are also giving exam for signals and system.
yeah, that's why I just trying to make sense of both together. Okay,
So
so
total of how many courses you have done, you have sent me. Like it's
oh
brilliant.
I have already did personal this principles of communication two last semester two.
Hmm.
Prerequisites I'm doing later.
No,
Okay, because
no worries.
frankly, I said, madam, I have not understood. I understood what it is, but intuitively I'm uncomfortable. So I want to, because I have gone through toughest subject. Now I'm going through the basic subject. So I should feel comfortable at the end of this exam. That's what I feel. So
Yes, and in practice, all we are doing is a digital modulation. So I think that
yeah,
subject is
yeah,
more tough.
yeah. I'm trying to understand that. That's okay.
I think
So
next semester, if I take,
Ma'am,
yeah, yeah, yeah.
ma'am, when will that course will start? That communication second part that sir is referring to?
Yeah, I think it will start this semester. This semester,
Okay.
you are having exam on 24th, right? So on
Yes, ma'am.
24th, after
No, not
24th,
24th, ma'am. Which exam, ma'am? 24th? No, it is on 29th, 29th of April.
29th of April. Okay, okay, okay. So, okay, 29th of April. So, after that, the semester will begin, and you please, I'll just suggest you to take that course as well. So, if we, I
Yes,
think
ma'am.
I can be the
It is
TA for
actually
that.
very interesting. It is very interesting course. One of the most interesting course.
You have taken that? No, this is the
No,
first
ma'am.
NPTEL.
I, this is the first NPTEL,
हाँ हाँ
but
ये
this communication engineering, I'm liking this subject actually very much.
in fact, Aditya sir courses there are four are there. All are excellent. And also there is another professor in IIT Bombay, Professor VM Gadre. So Gadre sir and Aditya sir, I found the best courses on DSP, signal processing, communications.
Okay.
Okay.
What about probability course? Have you taken any probability course? I'll just suggest you to take one probability course in next
I
No,
have
no,
semester.
taken.
ma'am. Please suggest name of the professor also.
So I think KG Krishna sir have taken.
Sir, I share my experience. I have taken two courses of different faculty members, and I failed. Okay, I don't think that you would fail because one is probability for electrical engineers. I took from IIT
Madras.
Madras, and
हाँ.
other one is probability for computer science. I took from IIT Kanpur. So
Both are the
both are
toughest.
abstract. Both are abstract. Both I failed, but I spent 80% of my time only on that. Okay. But I found there is another course, probability for electrical engineers, taught by
IIT
this.
Delhi.
No, IIT Madras only, which is applied, more practical. This is Andrew Tangaraj, sir. Excellent.
Andrew. I'll also take one course.
So,
Andrew.
Andrew,
yeah,
Andrew
so,
sir. Okay.
yeah,
IIT Madras.
suggest you take Andrew Tangaraj, sir, course. He is excellent. Okay,
And
I'm going to
Okay.
take that next semester.
I will also take. Actually, you know what? In research, like everything is probability, so you cannot escape from probability any time in the future as well. And if the communication system comes at that pace only, machine learning, everything comes at that probability concepts only. So it's good. So that sir taught what stochastic process and all those. This in that course you have taken.
No, madam. Only the basic of that sigma algebra, actually theoretical. Okay, most of it is probability theory,
Okay.
sigma algebra and theorems and proving theorems. So that's why it went above my head. So not much applied. But what I was told is there is exactly similar course, probability for electrical engineers by Andrew Tangaraj sir, in IIT Madras. That is more of practical, not
Okay.
theory.
Okay, sir. I will join it next semester.
Okay. So that is more. Madam, now coming back to our discussion, there is another thing. There is a frequency of the shifters. Okay, now we understood modulators.
Yes,
Frequency
yes.
shifters. Shifting in time domain, shifting and frequency domain. Can you just relate? Suppose shifting in time domain is T to T0,
Yes, yes, yes.
and that corresponding in the frequency domain, how it happens. For example,
So you know this xt minus t not sorry x suppose xt corresponds to this x of f.
uh,
Xt minus t naught corresponds to e power minus j 2 pi t naught
Yes,
x.
ma'am. Phase will change, right? Phase of.
Yeah, yeah. So what I'm
okay,
trying to do,
okay,
the x f will also be there, right?
yeah,
T naught f.
F will be there.
So this one. So this phase will be multiplied to this one. So what is happening here in amplitude? For example, if you take amplitude of this, suppose you have x dash f. So magnitude of x dash f is simply x of f, right? If you see the phase of that, how will you define phase? So phase of x dash f is simply but the sum of minus 2 pi t naught plus x of f.
Okay. Okay.
This is how the
Phase
phase.
vector.
Yeah,
So,
yeah,
yeah, it's a wait a minute, interesting.
yeah.
So, in a time domain, if we shift in time, it is equivalent to phase shifting in the frequency domain.
True.
Okay.
Similarly applies for frequency domain. You know, this if you just here it is not the space. So suppose if you have this x minus f naught, what will it corresponds to? It will have e power j 2 pi t, sorry, 2 pi f naught t
F not G.
xt,
Okay.
or xf corresponds to xt. So this is the foundation of
Yeah.
phase shift.
Yeah. Right. Shifting frequency. So, basically, modulation, frequency modulation is nothing but shifting in frequency, right?
True, true, true.
Okay, that's why in the FM computations we always see x of f minus something, f minus
F
f.
minus F. Yeah, yeah, yeah. In fact, have you seen this one? Suppose this is a LTI system. This one, yn is equals to alpha xn plus 1 minus alpha yn minus 1. So if you just take the jet transform of this, because in discrete system we generally take jet transform. So x of z 1 minus del z power minus 1 y of z. So here also this minus 1 corresponds to z power minus 1. What I am trying to say, which is simply h of z. So what is that? It's
That is a frequency
alpha
response.
1 minus alpha z power minus 1. So this is h of z. So what I'm trying to say, so you are making it recursive with some phase shift and adding it to have a feedback system. So it is a recursive system. You were saying na RRI, IIR, sorry,
Right.
impulse, infinite
Yeah.
impulse response.
IIR filters are recursive. Yeah. They have y things. Y is
Why
equal to
things are that is corresponding to feedback.
yes. Yeah. Always recursive things have feedback loops. Yes.
So what is I'm trying to say? So you are taking the sample before that, and that sample is using for the future prediction using the n minus 1
Yes. Causal.
causal. Yeah. So this is frequency shift, phase shift.
And next is scalars. Frequency scalars. Okay. There is nothing like time scalar, but only frequency scalars.
Scalars. Okay.
Frequency are
Okay.
multipliers.
So yeah. So suppose xt corresponds to x of f, then
Yes.
x t by a corresponds to I think x of af. This
Yes.
is
That means you're scaling.
t by a. I am not sure. Question, am I correct?
No, ma'am.
This-
One by mod A factor will come here on the right side. 1 by mod A. Here multiply. No, ma'am. Here you multiply by xt being scaled by a factor of a, right? So here we will multiply by mod of a on the right side. This is spectrum magnitude. will be
Here na,
multiplied by-
here na.
No, ma'am. I think it will be multiplied by mod a because here 1 by a is being multiplied na in the time domain.
Acha, sorry. Here. Multiplied by mod. Yeah. So basically, in frequency it will be scaled, and in time it will be compressed. This term I was not remembering. So so what is this? This t by a. So if you have xt as suppose this one, just take xt. This is t, and this is 5. Suppose this is 5 minus 5. So xt by a is what? A is 2. Suppose. So it will be 10 minus 10.
Okay.
So this is 10 and minus
Yes,
10.
ma'am. And a spectrum will be compressed in the
Compressed. So
frequency.
if you expand the spectra in time domain, the spectra in frequency domain will be compressed and vice versa. So this is all about the scaling in frequency and time domain, sir.
Okay. Yeah, I see. Actually, I am referring to frequency multiplier in somewhere in FM modulation. We have to scale the frequency. For example, whatever signal we give with the frequency of f, we have to have 2f or f square or f cubed.
Yes, sir.
Yeah.
So just look this expression from the other side. We are doing the same, I think. Here.
F square. How do you get f square? Frequencies.
The f square. Okay. F square, it won't be, sir, scaling. It won't be scaling, sir, if we are having the square of the spec. No, square.
That is something called multiplier, frequency multiplier.
It is frequency multiply. It's not a scaling. So
Yeah, multiplier. Yes. If you have signal F input, I wanted to get 3F output.
it's a scalar multiplication, sir. That is, if we are having 3f, but f square. I have to check.
I may be making mistake. Okay, so I had to refer to the book. Okay, so,
Yes.
that is not an LTI system. That somewhere it's mentioned. That is
Yeah, f square is somewhere.
not system. Okay.
That will not be linear, sir.
Yeah, certainly not linear. Certainly not linear. Okay. Pass band. Yeah, band pass band. Okay, pass band I understand. Pass band is nothing but high frequency filter, right?
Pass band, yes.
Okay. Band pass.
So pass band is basically band pass filter, but high frequency filter is this one.
Is the same, right? Pass
No.
band
This
pass
is HPF.
Uh,
This is band pass. So it is having only one cutoff frequency. After that, it passes all. But a band pass filter is having two cutoff frequency, FC1 and FC2.
Okay.
Hmm.
Okay. And LPF also has two frequencies. No, only one.
No, one only. It will pass up to this.
Okay.
The band pass and stop band will have two frequencies.
This is LPF.
Oh.
In frequency also filters also we don't consider negative frequency. So I think only two of you used to join the session. So I want to know in the last session and one more session I would like to take. So please let me know the content of that so that I could take because the questions I think you have already solved, and if you have some particular questions which seem difficult to you, then please let me know so that I could deal with that. Otherwise, I was making the table of this difference. I just want to make that the time is up that time. So Fourier transform versus Laplace transform versus Z transform versus Fourier series, where the sigma term is used, where it is not used, and where we consider the stability issues and all. So you should know all about that. So I will take this in the next class, most probably. Yes, Kushi, say.
Ma'am, I think in the remaining sessions, what we can do that just take some quality questions so that we
Yes.
can revise maximally the concept
So
of this article.
see, yeah. I want this next class is on, I think, 22. Yeah, it's on 22. So 22 if we have. So basically, I'll just want you to revise all the concepts of that. And in that, in 22, let us see where that concept difficulty is there. And then after that, one more session I'll take because I have to take 25-hour class. Before that, if you are having exam on 29, then we can take on 25 or 26. and then some rapid questions and all, so that you will remember all those formulas and all. So I think we can cover it up like that. And the quality questions, you are
Okay, ma'am.
saying how to check whether what is that quality
No,
question.
ma'am. Actually, this quality question, ma'am, only you can tell us, right? Because you have more experience.
Okay,
You
okay,
have
okay.
more experience.
See,
Huh.
what
Okay.
are the most confusing questions and tricky questions?
So I'll just tell you that I have taken I have done one good course of Aditya Jagannatham sir, and also have done some courses, but I'll just let you know that the question levels will be so easy, and some questions will be directly from the assignment, and some questions will be directly from the formulas. That type of questions you can expect, the 70% questions, not 70 but 65% questions definitely. The remaining some of the questions were can be difficult, like the spectrum
Ma'am,
drawing and all.
actually, it will be better if we discuss the remaining 30% type of question.
20.
That will be more beneficial. Yes,
Uh,
ma'am.
okay. Then I'll take that questions type of questions, and then fine. Then we will meet on 12th. Sorry, 22. 22 is the next, I think. Yeah, 7/22. So we'll meet on that, and it's very appreciated that if you can mail me some of your doubts so that we can deal. And today we have discussed a very good things like negative frequency and all. So I think okay. So, okay
Yes,
then,
ma'am.
yeah, then if you have any doubt, then
We
let me
can.
know. Yeah,
Sure, ma'am. Sure.
okay then we can stop this session now. Yeah.
Okay,
Okay,
thank you,
thank you, ma'am.
madam.
Thank you.
Thank you, ma'am.